In this online lecture, we're going to be looking at carbenes and polymerization. In most of the other previous lectures, we've looked at related reactions in every online lecture, but in this one, we're going to be looking at carbenes, which form cyclopropanes, and we're going to be looking at polymerization, which forms long chains of molecules. So they're really carbenes are a highly reactive species that form cyclopropanes. One way of looking at it is to chop an alkene in half, and you would make two carbenes if you did that. And then this double bond would be cut in half, giving you two free electrons. One way of looking at this is to consider that to be a non-bonding pair, or you can have it so that there are two single electrons in separate orbitals. There's evidence for both of these occurring. If it's a single non-bonding pair of electrons, then they have opposite spins, and if they're two single electrons, then their spins would be paired. And so we see evidence for both things occurring. The key thing is to understand that the reaction of a carbene with an alkene is that it forms a cyclopropane. And one way you can look at this is to say these two electrons actually reach out to these two carbons, and that the double bond in here, the pi bond, breaks open to reach out and bond back on either carbon. How do we form them? Well, one carbene that we can form is called dichlorocarbene, and it's formed by taking chloroform and treating it with strong base. When we treat it with strong base, this chloroform is slightly acidic, and the strong base can pick up a proton off this, and then that leaves a non-bonding pair on this carbon. Once that non-bonding pair forms here, a chlorine can leave with a negative charge. Notice when it takes these electrons and leaves, it takes a negative charge away. And what does it leave? A neutral charge in this highly reactive species. This highly reactive species then can react with an alkene to form a cyclopropane here. So here are the conditions again: chloroform and a strong base, potassium hydroxide. The strong base pulls a hydrogen and a chloride off of chloroform, giving the carbene, the dichlorocarbene. That then forms the cyclopropane, in which the chlorine has those two, the carbon has those two chlorines on it. And the byproduct of this is then potassium chloride and water. They're not showing the water that would form also. Okay, if I look at cyclohexene doing the same thing, you'll see we form a cyclopropane ring, and of course there's those two chlorines on it. One thing to notice is that it must join on one side of the double bond. There is no physical way for this to bond to the other side. And the stereochemistry of the alkene is preserved. Because it is syn addition, you have the carbon forming a cyclopropene right here. Notice if it cis in the double bond like this is, it's going to be cis in the cyclopropane ring. So if this was a trans 2-pentene, then the methyl and the ethyl group would be trans on the ring to each other. Another type of carbene reaction that we have is something called the Simmons-Smith reaction. It gives you something that is equivalent to a carbene. This is a carbenoid. This is not going to really be a carbene. It just acts as if it were a carbene. Let's look at how this is made. The first thing that we have is diiodomethane, and diiodomethane will react with this zinc-copper alloy. Basically, it is zinc with some copper added to the surface of it to activate it. The zinc does something really interesting, and what it does is insert itself into the carbon-iodine bond. The resulting compound, this right here, will act as if it were a carbene. It's carbene-like, and we say it's a carbenoid. So when it goes and reacts with an alkene, what do we make? We make a cyclopropane ring. Okay, what alkene and reagent would you be needed to make the product below? Look at this. This is trans 1,2-dimethyl cyclopropane. We've been making cyclopropane rings, so draw the structure and try to figure out how you could make that from an alkene. Well, the product that we want to make is this right here. You can see there is one, this is the cyclopropane, and there's 1,2-dimethyl, and it's trans. Well, we've been seeing that we can add carbenes to alkenes. What carbenes can we have? A dichlorocarbene or a carbenoid that it has 2 hydrogens on it. Well, the only way we could make this is to have this be added onto an alkene, because we can get this from the equivalent to the carbene with 2 hydrogens on it. So I know I'm going to be using the Simmons-Smith reagent, that is diiodomethane and the zinc-copper alloy. So now I have to think about what alkene I need. Well, if I cut this off, I'm going to have a double bond down here. And you can see there would be a methyl on this side and a methyl back that way. Well, that means that they have to be on opposite sides of the double bond. So what I am seeing that I need is that I need this alkene, 2 methyls opposite a double bond, opposite being trans on a double bond, and this reagent. So what reagents would you need? Trans, 2-butene, and zinc, well, that should be the zinc-copper compound, and the diiodomethane. So what alkene and reagents would be needed to make the product here? Cis 2,3-diethyl 1,1-dichlorocyclopropane. Okay, the first thing you need to do is draw the product that you need to make. If you look at this, you can see which part of the cyclopropane could come from a carbene. It's this part. We've seen that we can make a dichlorocarbene from chloroform and a strong base, potassium hydroxide. So now that I know that that's what I need to make the carbene, I can look to see what does my alkene need to be. I can see it's going to have 6 carbons, so it's going to be hex, and 1, 2, 3, it's going to have to be a 3-hexene. That 3-hexene is going to have the ethyl groups on the same side so that the carbene can give you the cis cyclopropane. So these are the reagents that you need. So what do you need? Cis, 3-hexene, potassium hydroxide, and chloroform. So what alkene and reagent would be needed to make this 3,4-epoxy hexane? Okay, to make the 3,4-epoxy hexane, this isn't a carbene. This is from a previous online lecture, but it's good to review things like this and throw them in there to make you think about what you're doing. This has to be formed from a peroxy acid. So what are we going to have? An alkene, so the double bond's going to have to be here, and there's my alkene. And any peroxy acid, you could use MCPPA, PBA, or you can use peroxyacetic acid, or any peroxy acid will give you this epoxide. We're going to be talking about polymerization now, and polymerization is a very important concept. Our world is full of polymers that we call plastics and rubbers and things like that. And our biochemistry is full of polymers. The whole idea of a polymer is that you have many molecules that we call monomers that make up this long chain. Here's an example of a polymer. Cellulose is a polymer of glucose. So when we look at cellulose, it's just this big long chain of a glucose molecule attached to a glucose molecule attached to a glucose molecule, on and on, where you have potentially thousands of glucose molecules all attached in one long chain. We call glucose the monomer because it's the unit that makes up the individual links in this long chain. There are other biological polymers. For instance, proteins are polymers of amino acids. This is an amino acid, and that's a big long chain of amino acids, and we call that a protein or a polypeptide. And our nucleotides, our RNA and DNA, are polymers of nucleotides, so that we see nucleotide chained up to another nucleotide, on and on and on, until we see one big long chain of them. We're going to look at the simplest type of polymer that there is, and that is one that is of ethylene, just this tiny little molecule, 2 carbons double bonded to each other with hydrogens. What we can do is take this and we can link them together, and when we link them together, notice the double bond goes away and each end of the double bond gets hooked to another ethylene, and we call this polyethylene, and it makes a huge long chain. How do we do this? We do the linking by causing a free radical to be generated within the presence of the ethylenes, and then the ethylenes pick up that free radical and start a big long chain reaction. So a common free radical generator is something called benzoyl peroxide. When you heat it, what happens is it makes a benzoyl free radical. The free radical is right here on this oxygen. You see this one right here. What these little arrows are showing is how there's resonance of the free radical around this ring, and there's some stabilization from that. But this is where we have this free radical from the breaking of this bond. This is a peroxide because we have 2 oxygens bound to each other within a molecule, and it breaks right here and gives a free radical on this oxygen. This is an abbreviation for that free radical, and what happens is you get it to add to an alkene, and when it does, this forms a bond right here, and then this jumps over here and gives a free radical on this carbon. And this is a propagation step, like we've seen before. 1 free radical plus 1 neutral molecule leading to a free radical on the other side is called propagation. And you notice this then can do the same thing to another alkene. Instead of the benzoyl peroxide free radical, you could have this adding to a free radical and adding another methylene group on it. So what happens is you get this big long chain of all these ethylene groups all stuck together. And the R is just saying big long chain over there. And finally, at some point in time, 2 free radicals will join together and you get termination. And we can do this with other alkenes. That was polyethylene by taking ethene or ethylene and polymerizing it together. But I can take propylene, this is also called propene, and I can cause it to be polymerized. Notice, here are the 2 carbons in the double bond, and attached to one of the carbons is a methyl group. Here are the 2 carbons in the double bond. Here's another 2 carbons in the double bond. You see, this is one propylene. This is another propylene. This is another propylene. This is another propylene. And you see it makes a big long chain of all those propylenes all bound together. Here's styrene. Here's the double bond that's going to participate in the polymerization. Okay, so these two carbons are found here. Here's another two carbons. Here's another two carbons. And here's another two carbons. And this is called polystyrene because this is styrene. Okay, you need to be able to take an alkene and determine what polymer will form from it, or look at a polymer and determine what alkene made it. For instance, if I give you this alkene, what polymer would form? So to figure this out, the first thing you would do is draw several of these alkenes, 1,2-dichloroethylene, next to each other. And so now what you see is that we have one here, one here, one here, and one here. Now what you need to do is erase one of the double bonds from each of these, and then go ahead and put a bond connecting them. And then what we'll have is, of course, the ends will be connected to something, so we show that by showing that they're connected to something. And so what would we see next? After we erase the bond here, notice it's erased, we connect it to here. And this is saying it's connected to some other junk over here. That's all that this is saying. So then here's the monomer. The double bond is gone, and now there's a bond between this and this monomer. The double bond is gone from it, and now it's connected to the next monomer. The double bond is gone here, and now it's connected to the next monomer. And then here's the double bond, and the double bond's gone, and it's connected now to some junk over here. So you see that is showing a picture of the polymer, and that's how you would demonstrate what polymer would form. So look at this and try and figure out what polymer would form from this. Okay, if we look at this, you can see that we get this is one monomer right here. We've erased the double bond in here and connected it to the next. One monomer here, erased the double bond, connected it to the next, and all the way across. This is actually called polychloroethene, which is given the symbol PVC, which I'm sure you've seen before. Here is another one. What polymer would form from this monomer? Again, it's just carbon. Here's one monomer linked to the next. The double bond disappears when you connect it to a neighboring monomer, and so you get this all the way across. It's just carbons bound to carbons with fluorines attached. This is polytetrafluoroethylene, which is given the brand name Teflon, which again I'm sure that you have seen before.